Okay, we're back at it. We've got a lot to cover today. So let's get into it. We're going to talk about alkylation of the alpha position. So alkylation of enolates. In general, what we'll do is we'll take a base. We're going to deprotonate our alpha position, generating an enolate. And then we're just going to attack alkyl halides in an SN2 reaction and make a carbon-carbon bond. So since this is an SN2 reaction, we're going to be limited in the substrates. Primarily, it's going to be methyl halides or primary halides. Secondary halides react poorly, and tertiary halides, since it's a SN2 reaction, don't react at all. And we can actually use other leaving groups besides halides. We can use tosylates and other leaving groups. So it's simply an SN2 reaction with an enolate as our nucleophile. Now we can't use sodium hydroxide as a base. And the reason for that is if we used OH minus, we would set up an equilibrium that favors the carbonyl, and we would only have a small amount of enolate in solution. And then if we happen to throw in our alkyl halide, the most likely reaction would be the hydroxide attacking our alkyl halide. So we need a better way to get our enolate. And in this case, we're going to use LDA again to get our, again, 100% quantitative deprotonation of our enolate. So the first step is just to add the LDA, wait until you get the enolate that forms. Again, you can draw it in either of the two forms shown here with the negative parked on the carbon, or you can actually show it drawn in the most stable or the major contributor to the structure resonance form. And either way you decide to draw it, the next step of the mechanism is simply an SN2, attack the backside of that alkyl halide, kick off the bromide, and you've now alkylated at the alpha position. You can also alkylate esters, as shown down here in the second from the bottom example. So we can actually alkylate at this position here. We're going to use LDA as well to deprotonate. Aldehydes are not good reagents to try to alkylate. And we'll talk about that a little bit later. There tends to be a competing reaction there. And again, these enolates really aren't limited to just carbonyl compounds. Anything where you can deprotonate and have some resonance stabilization by an adjacent group can actually form these reactive carbanions. So next to nitrile, you can also deprotonate and use that as a nucleophile and alkylate there as well. So if we happen to have a molecule that is differentially substituted, so in this case we actually have a tertiary carbon here, and on this side we've got a secondary carbon, and we mix it with LDA. The question is, well, which enolate am I going to form? We answered this question a little bit earlier when we did the aldol reaction. We did that reaction at room temperature, and we tended to form the more substituted enolate. So this would be the more substituted double bond. That would be more thermodynamically stable. But notice that this one is a less substituted double bond and comes from pulling off the less hindered alpha proton. So if we were judicious in our conditions, we should be able to select for the less hindered site over the more hindered site. And we can actually do that. So this is what's called the kinetic and thermodynamic control. So kinetic control, we're going to pull off the most accessible proton. So the least sterically hindered alpha hydrogen. And we tend to do this at low temperatures, -78. And that gives you the less substituted enolate. If you do this at room temperature, or even 0 degrees above -78, you get the thermodynamically formed enolate. It tends to be the most stable, the most substituted, and it gives us the enolate in the green box there. So we can actually control which side we alkylate. We can alkylate at the less substituted under kinetic control, low temperature. So this would be low temp to get alkylation at the less substituted. And if we wanted to alkylate at the more substituted site, we would run it at a higher temperature. So we actually have options here. And again, the key is the degree of substitution that the enolate exists in. So if we have the less substituted enolate here, we can form that under low temperatures. If we have the more substituted enolate here, we tend to form that under higher temperatures. And so we've given you an example down here. And in fact, we can actually control it a little bit more. LDA is somewhat of a sterically hindered base. And so it would favor the more accessible side, the less substituted side. So if we use a hindered base and a low temperature, we can get the kinetic enolate, fastest one formed, the most accessible proton, and alkylate at the less substituted side. If we use a smaller base, such as NaH, that is able to get to that more hindered tertiary proton here and run it at higher temperatures, we get the thermodynamic enolate. Notice we substitute at the more substituted carbon, where the kinetic control, low temperatures, we substitute at the less substituted carbon. So watch for the temperature and the base, and that will help you decide where to put the alkyl group. Again, the major consideration is actually the temperature. So under low temperatures, the less substituted site, higher temperatures, the more substituted site. Now, we don't always have to use LDA. If you remember when we talked about the base needed to deprotonate, we said in some cases you can actually get quantitative deprotonation of the alpha proton using a weaker base. So here we're going to use sodium ethoxide. We don't need LDA, and we're going to get 100% deprotonation. We're going to use this molecule over here that is known as diethylmalonate, known as malonic ester. And we don't have to use LDA since it is a doubly resonance stabilized enolate. We can actually go and deprotonate it with a weaker base and get 100% enolate. So if we use sodium ethoxide in there, we can get 100% of that. And then what we can do is alkylate at that position. We could then go and add whatever alkyl group. Again, it's an SN2 reaction, so we're limited to methyl and primary halides. And now we've added an alkyl group onto this malonic ester. Now, what's really interesting about this is if we follow that up with some acid and heat, like we see in step 3 here, all of a sudden the molecule that we get looks very different than the one that we started with. So what we end up with is really just an acetic acid that has some R group off of it. And you may be asking, well, where did all the atoms go? And we'll be talking about that now. So this is known as the malonic ester synthesis. We take this big molecule, diethylmalonate, and those atoms in yellow are the only ones that end up in the final product, as well as the alkyl group that we add there. So there's a lot going on here. So first of all, let's just talk about alkylating these doubly resonance stabilized enolates. And that is shown in the middle of the page there. We can take sodium methoxide. Notice that we're using the base that corresponds to the ester. This is much like the Claisen condensation. So we're going to have the base that is similar to the ester. Again, a side reaction that's always occurring is this transesterification reaction. That OET minus is attacking that carbonyl and kicking off another OET minus. So therefore, you want to make sure that the base that you use matches your ester, so in the end, you don't see any difference in that ester. But the productive reaction is actually the deprotonation of this doubly resonance stabilized enolate, and we park those electrons there. And again, it can resonate both ways. And so we get 100% of this enolate, and we didn't need to use LDA, a strong base. Then what we do is we treat it with an alkyl halide, again, preferentially a primary or a methyl alkyl halide. And we've now substituted at that alpha position. But the question is, well, where do all those other atoms go in this malonic ester synthesis? How do I get to the point where I really just have a acetic acid and that R group? Where do all these other atoms go here? Okay, keep that in mind because we're going to talk about it. But first of all, we can actually alkylate these malonic esters twice. We can deprotonate, and that gives us an enolate, and we could add on one R group. And then we get this product here. We would need to purify it. You can't just do this in one pot, but you purify it. So this product here is the same as this starting material there. And what we're going to do is deprotonate it again with a base. We get the carbon ion, and we do this reaction again. We're going to do an SN2 reaction, attack that primary alkyl halide, kick off the leaving group, and now we have a dialkylated malonic ester. So in these times, and you're looking for something that may be useful, since you have to work from home, this is a reaction that is useful in the synthesis of barbiturates. We actually used to do a very similar lab to this in this top box there. We would actually take diethylmalonate and we would take urea. You'd take sodium ethoxide in ethanol and you'd heat this up for a 4-hour reflux. And for some reason, the students just didn't find that very entertaining. I thought it was pretty cool because you would get barbituric acid out of it. Now, barbituric acid is not pharmacologically active in our bodies, so we could actually make it in lab. But to actually go from barbituric acid to a pharmacologically active molecule isn't that hard. As you can see in this bottom box, what you do is you just take diethylmalonate and you do a dialkylation. And so you put, in this case, 2 ethyl groups off of there. And then you do this exact same reaction that we used to do in the lab, where you just mix urea with your new product, and you would actually get barbital. And so these barbital and these other examples over here used to be the drugs of choice in the 70s. So they're referred to as barbiturates, they're downers. So once your Hollywood stars got hopped up on cocaine and methamphetamines and needed to come down, they would take barbiturates. So quite a few people ended up dying. Elvis was one, Marilyn Monroe was another one. There's an interesting Wikipedia page that lists all the people that died from overdosing on barbiturates. And they still give barbiturates today in surgery. They can be sedatives, and they just don't have as much use since diazepams such as Xanax and Valium are now more commonly used. So here we're showing you how to make several different barbiturates. And in fact, you can see their street names. Like I said, these were very common in the 70s, 60s, 70s. So these are known as blues, bluebirds, blue heavens, nimbles, yellow jackets, yellow submarines. I wonder if that has anything to do with the Beatles. And then pinks, reds, red birds, red bullets. I believe those names come from the color of the pill that they used to be. And these all have different effects. So some of them last longer than others. They all go through this chemistry that we're talking about, though. This is what's important, is they start with diethylmalonate. Notice they deprotonate with the base. In this case, they add on an ethyl group. They deprotonate with the base, and then they add on this isopentyl group right there. And that gives you amobarbital. Here, we add a base, add on an ethyl group, add a base, and then they add on this other group there, and that gives you pentobarbital. Here, add a base, add on this group with an alkene in it, add a base, add on this other alkyl group, and now you got secobarbital. So we're not going to be making barbiturates. We'll stop at this dialkylation of diethylmalonate there, but this is a useful reaction to make drugs. As I mentioned, though, it's not just making that diethylmalonate that's interesting. What happens is we can actually make a substituted carboxylic acid, specifically acetic acid. Now, if we just tried to take acetic acid and do this chemistry and add on an R group, we would run into lots of issues. First issue that would run into is if we tried to have a base and we were hoping to deprotonate that alpha proton, that base would deprotonate the acid. As we saw back in the Helmholtz-Zielinski reaction, carboxylic acids aren't very good at forming enolates. So we can't directly go and form an enolate on a carboxylic acid. And the reason for that is we deprotonate the carboxylic acid to form a carboxylate. That tends to resonate into that carbonyl and make this alpha proton less acidic. In fact, if we were able to pull off that alpha proton, you could see that we would end up with a dianion, which isn't going to be very stable. So that is not a very good route to substitute at carboxylic acids. So just like we did in the Helmholtz-Zielinski reaction, we had to play a trick. We had to turn the carboxylic acid into an acid bromide in that HVZ reaction. So here we can actually make a product, and you notice in the bottom right-hand corner, you can actually see the product that we're making. You can see that it is just a acetic acid or ethanoic acid that has a R group. And so we're going to have to do that, but we're going to use some tricks. You could almost view this as some protecting group chemistry. We have a group on there that we're going to be able to remove. So let's start here with the monosubstituted diethylmalonate. We made this just by deprotonating the diethyl ester of malonic acid and then adding an R group. In fact, I'll go back just to remind you how we got there. It's this top box right here. So what we did is we just deprotonated the malonic ester and added a single R group. Once we add that single R group, what we do is we mix it with H3O+. If we mix esters with acids, we get hydrolysis. This is back in your carboxylic acid chapter. And what we end up with is a dicarboxylic acid that you can see over here. So that dicarboxylic acid actually does something interesting when you add a little bit of heat to it. It actually does a decarboxylation reaction. So this dicarboxylic acid, this structure down in the left is the exact same structure. They just drew it a little bit differently. All they did was rotate around this bond and draw out this OH bond right there. So again, these are the exact same structures, just drawn in different conformations. And what happens when you heat that up, you undergo this paracyclic reaction where you transfer a hydrogen and you decarboxylate. And so if we just walk through, kind of a fun reaction, we pull off a hydrogen, that breaks this hydrogen-oxygen bond. And then the key is it actually breaks this carbon-carbon bond right there. So I'm going to draw in the CO2 that is formed from this reaction. So this C double bond O, and that O turns into CO2 right there. And in fact, every time you breathe out CO2, which is with every breath that you take or you breathe out, you're releasing CO2, and this is the mechanism that you generate CO2 through the TCA cycle, the tricarboxylic acid or the citric acid cycle. So this is a reaction that is useful in our bodies. We release CO2 through this type of decarboxylation. Now we're not done because we end up with an enol. And we've talked about this many times before. When you have an enol, that's not really the stable form. Enols tend to tautomerize. And again, I have a quick and dirty way, Stephenson accepted method to show that tautomerization. The double bond pulls that H off. Those electrons collapse down there. So we essentially transfer an H to that alpha position. Remember, tautomerization is a rapid interconversion of constitutional isomers. And you can see by the equilibrium arrow that we are heavily favoring the carbonyl form of this. So what we've done is we've actually added an R group to acetic acid. And this is what's known as the malonic ester synthesis. So you can see an example here on the top of the malonic ester synthesis. We start with malonic ester, we deprotonate it, so we would end up with a carbanion there. That carbanion then goes in and does an SN2 reaction, kicks off the leaving group. And then the key to look for is this acetic acid here and this R group there. So once we formed the enolate, we've come in and attacked and we've kicked off that bromine. So over here to the left, I'm going to draw out the product from step CO2. I'm just going to abbreviate the benzene ring as an R. Then what I'm going to do is, once you added the H3O plus, I'll draw the product of that reaction. That is going to give you the dicarboxylic acid with the R group that we just added. And then the heat is going to give us that final product there, indicating in the green box the carbons that came from the malonic ester, and I'll highlight those from the malonic ester in a green box as well. So all those in that green box there show up in this green box. So to finish up the mechanism, what I'm going to do is just redraw this product. There's the R group that we added. I'm going to draw out my other carboxylic acid in a little bit different conformation. And what we're going to do is pull off that H here, collapse those electrons, break that bond, and that is going to give us this acid enol. There's the R group that we added. And you can see that we've got an enol, and again, we're going to tautomerize and finally get to our product there. So one of the reasons this works is because a carboxylic acid with an adjacent carbonyl on the beta position can actually be a good leaving group. If I just happen to have in this box here that H leave, it would park electrons on just that carbon atom, and that's not very stable. Even if I just had a carboxylic acid and it dropped its electrons in, it would park its electrons on that carbon, and that's not very stable. So these beta carbonyl acids, which is shown here on the bottom, they actually end up having very good leaving groups. The enolate is actually the leaving group. So if you watch this, those electrons come in here, form a double bond. That double bond is going to form right there. Since I'm forming a double bond here, I need to break this bond. Now I need some way to stabilize those electrons that are coming out of that bond. Now I can't just park them on a carbon. I actually need to move them up onto this oxygen. And so if you look, the leaving group from this reaction is actually an enolate. And the enolate can, again, tautomerize, well, sorry, has two different resonance forms here. Now, if we do this with an H off of here, what we would end up with is an enol that tautomerizes just to the ketone there. So kind of an interesting reaction where this beta carbonyl actually helps the CO2 be released from the molecule, and the enolate actually acts as a leaving group there. Okay, so this decarboxylation reaction, it's not just limited to the malonic ester. You should be able to identify where you have a carboxylic acid, and what you do is you just look next and see if you have a beta carbonyl. So I've got carboxylic acid on the alpha position there and the beta position. Oh, look, I've got a carbonyl. Therefore, when I add heat, that carboxylic acid turns into CO2 and leaves. We break this bond here, and we're now one carbon shorter. We've produced CO2, and we have just a ketone. Oh, carboxylic acid, alpha carbon, beta carbonyl. I heat that up, and it can decarboxylate, and I just make cyclohexanone. This bottom example here, so the third one down, if I heat it up, I actually just end up with propanoic acid there. And again, at the very bottom, showing you the mechanism for that. So we don't have to use malonic acid for this. We could actually use anything that has a beta carbonyl. So the examples that we just showed you are what are referred to as the malonic ester synthesis, and there is a partner in crime known as the acetoacetic ester synthesis. But before we get to that, let's just review the malonic ester synthesis and run through it. So we start with a diethyl ether of malonic acid. We deprotonate with a base that corresponds to the ester there. We have this doubly resonance stabilized enolate, and then we go and attack a alkyl halide. Again, it needs to be either a primary or a methyl halide. We then get our alkyl substituted malonic ester, and we add a little bit of acid and water. And again, just like we saw back in the carboxylic acid chapter, when we take esters and we add acid and water, they hydrolyze to their carboxylic acids. Remember, you can turn any of the derivatives into carboxylic acids just by acid and water. So we get a dicarboxylic acid here. And then the magic happens when we add heat, we get the decarboxylation. And so the decarboxylation, we're going to lose one of these carboxylic acids at CO2, and we end up with, and it doesn't matter which one you lose, so just to match the scheme, this one in green is going to be the one that we keep. And the one in orange is going to be the one that we lost as CO2. So that's the malonic ester synthesis, adding one alkyl group. We can actually add two alkyl groups, but in order to add two alkyl groups, we need to do it in two steps. A lot of students just want to do it once, but we actually need to do it twice. So notice we deprotonate, add the alkyl group, deprotonate, and add the alkyl group. And once we've done that, same process, we go and hydrolyze the esters. We end up with our dicarboxylic acids, and we added two new alkyl groups on there. And then finally, what we're going to do is heat it up. And again, when we heat it up, we're going to lose one of those carboxylic acids as CO2. So the one in green is the one that leaves. So if you ever see a question asking you to synthesize a molecule that has this acetic acid and it has R groups on there, that is accomplished through the malonic ester synthesis. As I mentioned, you don't have to use malonic esters. You can actually use other molecules. Oh, but before we get to that, let me show you one other trick that you can actually do. You can actually make cyclopentyl or even cyclohexyl carboxylic acids. So since we can actually alkylate malonic ester twice, we can take a dialkyl halide, we deprotonate, that kicks off that alkyl halide there. We'd need to add in the base, do the second alkylation again. So in this case, we're just doing a dialkylation. It just happens to be with a molecule that forms a ring. And then what's going to happen with this H3O plus in heat, again, we're going to hydrolyze those esters, and then we're going to lose one of those carboxylic acids as CO2. So kind of interesting way to make cyclopentane carboxylic acid through the malonic ester synthesis. Okay. I keep saying that there's other species that we can use to do this reaction. So up here is the malonic ester synthesis. The general outline, we have a base that deprotonates, add an alkyl group, hydrolyze the ester, and then we decarboxylate. And we end up with an acetic acid group with some R group. And again, we could add 2 different R groups there as well. So there's a variation on the theme that is known as the acetoacetic ester synthesis. That name comes from this molecule down here, acetoacetic ester. Now notice the only difference is this only has one ester. The malonic ester is a diester, it comes from a dicarboxylic acid. So we're going to do the same reaction. We're going to add on a alkyl group. So we first deprotonate and then add on an alkyl group. And so we would add on the alkyl group to that position there. Then what we're going to do is hydrolyze the ester, and then we're going to decarboxylate. Now what's unique about this one here is we actually end up with a substituted acetone. Now the reason that that works, I'll highlight up top here what carbons we keep from the malonic acid. We keep the alpha carbon, the carbonyl, and one of those oxygens. In the acetoacetic ester, we keep the alpha carbon, the carbonyl, and we actually keep that CH3. So malonic esters are essentially alpha substituted acetic acids, and the acetoacetic ester synthesis gives us alpha substituted acetones. So again, the overall transformation for the acetoacetic ester is we have an acetone here and we have alpha substitution. And so let's see how that works. We take our ethyl acetoacetate, or the acetoacetic ester right here. We're going to deprotonate. It is a doubly resonance stabilized enolate, so we get 100% of this enolate, and then it comes in and does an SN2 reaction. Again, we need either a primary or a methyl halide, and we have a monoalkylated acetoacetic ester. Now we could continue on with this, or we could deprotonate again, just like we did in the malonic ester. Deprotonate it again, add in a second alkyl halide, and get a dialkylated acetoacetic. So just like in the malonic ester, we can get a monoalkylated and then stop, or we could get a dialkylated. Either one of those that we choose, the process after that is going to be exactly the same that we saw with the malonic ester synthesis. So let's run through the mechanism completely. We're going to deprotonate that alpha position, do an SN2 reaction here, and then what we do is we hydrolyze the ester. Now in the case of the acetoacetic ester, we've only got one ester. The malonic acid, or malonic ester, we had 2 that ended up being 2 acids. This only has 1 ester, so we only end up with 1 carboxylic acid. And lo and behold, when we heat it up, we're going to lose that carboxylic acid. So again, what we end up with is an acetone molecule with that R group right there, and we're going to lose a CO2. So we lose the CO2, there's the R group that we added, and here is the acetone that we got from our acetoacetic ester. So again, just to help understand this mechanism, at top is showing how we get decarboxylation from essentially malonic acid. Malonic acid is a diacid. And again, the key is we need a beta carbonyl. It could be a carboxylic acid, it could be an aldehyde, it could be a ketone. We just need that beta carbonyl. And what we end up with is an acid enol, shown in the middle here. And then that acid enol tautomerizes. Again, the quick and dirty way of showing that mechanism. is drawn there, and we end up with a carboxylic acid. And again, we added an R group. If you have a beta keto acid, and this is what would come from the acetoacetic ester, the mechanism for the decarboxylation is shown. So this double bond would pull an H off there. That would form a double bond between that carbon and break this bond. That would then come over and kick those electrons up so we could pull that H off. We end up with just an enol, and that enol again would tautomerize just to a ketone. So to beat a dead horse, the malonic ester gives you a substituted acetic acid or ethanoic acid. The acetoacetic ester is going to give you a ketone. Okay. And for the acetoacetic ester, this R group would actually be a CH3, and then you would have your R group that you added. So those are a couple ways to alkylate either esters or even ketones. And we can actually do some interesting reactions. So if you look at this top reaction here, I'll give you a second to see if you can name it. Again, keep collecting those bonus points and take them home and show them to your mom so she'll give you that gold star. And if you happen to say that this top reaction is a Claisen condensation, you were wrong. It is an intramolecular Claisen, which is known as a Deichmann reaction. We talked about that in the previous lecture. And so the Deichmann reaction happens because we deprotonated that alpha carbon, and we come in and attack that carbonyl up, down, and we kick off that leaving group. And lo and behold, we have this interesting molecule. Now, if you look really close, what you see is a beta keto ester. You're always going to get a beta keto ester from a Deichmann cyclization. Well, if we take some of the things that we just learned, I should be able to hydrolyze that ester with H3O+. And yes, you can do that. And if you hydrolyze that ester, you get this beta keto carboxylic acid. So I'll give you a second to try to figure out what would happen if I heated up this beta keto carboxylic acid. And for an extra bonus point, name the product. And the answer is cyclohexanone. So from a Deichmann reaction, you can actually make cyclohexanone. So here's another fun example down here. We could actually take this product, which again is from a Deichmann cyclization, that would deprotonate at the most acidic proton, which is between those two carbonyls. We have the ester, we have that carbanion. We could do an SN2 reaction and kick off that alkyl halide. And now we've got this beta keto ester that we've added that benzyl group on. And when we add H3O+ in heat, this whole group right here would first be hydrolyzed to a carboxylic acid, and then the heat would cause it to be lost. And we end up with this interesting molecule right there. Okay, let's end it there. We've got maybe 1 or 2 more lectures to finish this up. We'll talk about conjugate addition reactions next. Just to prep you though, we're going to be using this molecule here as an electrophile. And before that lecture, see if you can remember how to make an alpha beta unsaturated carbonyl. I'll give you a hint. If you can't remember, go back about 3 lectures. We'll talk to you soon.